Hello there. This is an example that I wanted to post online for you, a video that gives some motivation for the need of measures of dispersion. Now, up to this point, we've talked about measures of central tendency, the mean, median, and mode, and how those give us a sense of the quote-unquote center of the data set. Well, what about measures of dispersion, this idea of a variance and standard deviation? What are these needed for? Why do we want these? And so I want to motivate the need for these terms or these quantities, as well as go through a computational example. Here's the example page that I'm going to work on, but before I do that, I want to motivate again the need for measures of dispersion. So suppose here we have an airplane here, and he's flying along, and he works for, say, FedEx, or maybe he's in the U.S. Air Force, and he has to, or she, whoever's flying, is dropping loads to the ground, and there's a target. Say this target here is at X, and they drop a load to the ground. All right. Well, you want the drop to be pretty close to the target. That makes sense. I mean, this is not the only example. When the UN flies in aid and they drop it from an airplane on a parachute, they want to be close to their target. When when firefighters are wanting to put out fires and they have helicopters or airplanes come by and drop water, they want the drops of those water to be on target. So this is an important example here. Anyway, so suppose this this airplane here, he drops a target, or he drops a payload trying to hit the target, but he overshoots it a little bit and it ends up there. Suppose he flies back around and he drops another target and it ends up over here. Ignore that. Suppose he comes around again. He's not driving, he's flying, and he drops another target or a load right there. Suppose he drops a fourth load right here, and a fifth load right here, and a sixth load right here. Well, on the average, if you think about kind of his average drops, he's on the average he's on the target. Okay. All right, well, suppose that's pilot A, and pilot B here is his competition. They're flying approximately similar airplanes, suppose, or these might be viewed as sharks. If y'all want to give me some airplane pictures, that would be fine. So, again, say airplane B here, pilot B is wanting to drop loads on target X. Suppose his first load is right here. His second load is right here. His third load is right here. His fourth load is right here. His fifth load is right here. His sixth load is right here. Well, on average, pilot B is with the target. He's got some too far and some too short of the target. Well, however, if you compare, so if we use just the averages, you would say pilot B and pilot A have their drops are equally as good. But even if you just look at the picture, you would say, well, no, I want to go with pilot B because he's consistently closer to the target compared to pilot A. In a way that measures this closeness that these drops are to the target can be done through measures of dispersion, and that's what the variance is. That's what the standard deviation is, measures of dispersion. So let me flip over here and come back to this this page here and actually do a computational example. So suppose here we're dealing with pilot A, and he has 6 distances. They're in tens of feet from drops from the target. So his first drop was 10 feet from the target. His second drop was 20 feet from the target, 30 feet from the target, and so on. So what I want to know is whose drops are consistently closer together. And the measures of dispersion tell me this. Okay, so I'm after this question: what is S squared and S? That's the variance, that's the standard deviation. Okay, now this is the variance of a sample, this is the standard deviation of a sample. This is the variance of a population, this is a standard deviation of a population. So we use different terms. Be sure you know the difference here. So I'm treating this as a sample, so I'm looking at S squared. S squared, you recall, is the sum of the deviations squared over n minus 1. Okay. Well, let's see. So what is n here? N is my sample size. I've got 6 data points in there, 6 drops. Now, to compute this quantity here, what I want to do is I want to compute each deviation. All right, so I'm going to create a table. It's got x sub I and x sub I minus x bar and x sub I minus x bar quantity squared. And so, making out my table here, my first observation is 1. That's xi. x1 is 1. x2 is 2. x3 is 3. x4, the fourth observation, is 3. x5 is 4, and x sub 6 would be 5. Okay. Again, this quantity right here, xi minus x bar, is a deviation, and I want to compute the deviation for each of these observations. The deviation tells me how far an observation is from the sample mean. Well, what's the sample mean here? We haven't computed that yet. But if you sum through these observations, sum through all the observations and divide by n, turns out you get 3. Well, let me back up a little bit. The sum of the x's is 1 plus 2 plus 3 plus 3 plus 4 plus 5 over 6. Let's see if we buy that. So here we've got 9 plus 9 is 18 over 6 there. That gives me 3. So x bar is 3. So when I look at the first deviation here, I have 1 minus 3. That deviation is negative 2. The deviation associated with 2 is 2 minus 3, and that is negative 1. The deviation associated with 3 minus 3 would be 0. 3 minus 3 is 0. 4 minus 3 is 1. 5 minus 3 is 2. Okay. Now what I'm going to do here is I'm going to take each deviation and I'm going to square it. So I take this value here, negative 2, and I square it, and I get 4. Negative 1, square it, and I get 1. 0 squared is 0. 0 squared is 0. 1 squared is 1, and 2 squared is 4. So I have my squared deviations. Now I'm in place to compute the sample variance here. So what I do next is I come back to my formula. Again, I'm looking at the sum of the squared deviations divided by n minus 1. Well, the sum of the squared deviations is simply the sum of these numbers here. So I've got 4 plus 1 plus 0 plus 0 plus 1 plus 4 over n minus 1. N here is 6, so I've got 6 minus 1 in the denominator. So what I have here is, let's see here. So I've got 10 over 5. All right, so that works out nicely. S squared is 2. So that's my variance. That is a measure of how close these observations are to each other. And when we interpret that in light of the example, that's a measure of how close pilot A's drops are to each other, or actually how close they are to the mean here. So if S squared is 2, that means that S is the square root of 2, and square root of 2 turns out to be, what's the square root of 2? 1.41, right? Okay. All right, so this is also a measure in the original units, S is, of the dispersion of these data points here. The standard deviation and the variance here. Now this is for pilot A. These were his drops. Now for pilot B, suppose these were the drops or the distances from the target for each of his drops. So we have 25 feet, 20 feet, 30 feet, 30 feet, 35 feet, 40 feet. Well, it turns out, I'm not going to go through the computation here, but it turns out that the mean for this data set is also 3. So what you might be tempted to do is see, okay, X bar is 3 here, X bar is 3 here. On the average, their drops are of the same distance from the target, but the average does not tell the whole story. The standard deviation tells us a little bit more. It tells us how close these drops are to each other, the concentration of the drops around the target. And so it turns out, I'm not going to go through the computation here, but S squared for this data set turns out to be, I want to turns out to be 0.499, and S turns out to be 0.707. So if you look at these, when I compare the variances here, clearly the variance for pilot B is smaller, and also the standard deviation for pilot B is smaller. In fact, it's about half of what it is for pilot A. So that tells me on the average they're the same, but pilot B's drops are concentrated or more concentrated than those for pilot A. And that's how I set up the example here, right? These drops are more concentrated with respect to each other and the target than these drops are over here. Okay. Well, I hope this was helpful for you in learning how to compute the standard deviation and variance, as well as understanding it.